welcome to another Spectrum Design Exploration. Tonight we are going to go over the robot for 3005, the Robochargers, our friends up in Dallas. They have been building pretty awesome robots for quite a while now, and this is one of their best ones last season. Start off, we're going to look at the game. We have quite a few new people who may not know what the game in 2023 was. The game is charged up. We'll go ahead and watch the animation, and then we can talk about it again. Let's turn down the volume first, make sure it's not too loud.
Welcome to the 2023 First Robotics Competition game, Charged Up, presented by Haas.
Two alliances of 3 teams each compete to score cubes and cones into their grid to charge up their community. The alliances earn additional points if their robots are docked to or engaged with their charge station. Robots start each match in their community and may be preloaded with either 1 cube or 1 cone. Each alliance may choose where to stage 4 additional game pieces. During the first 15 seconds of the match, robots are autonomous. Without guidance from their drivers, robots score preloaded game pieces, collect and score additional game pieces, and are docked to or engaged with their charge station. Charge station points earned during auto count towards a potential activation bonus. The grid has nodes specific to cones and cubes, and some where either a cone or cube can be scored. During the remaining 2 minutes and 15 seconds, drivers control their robots. Robots continue to collect cubes and cones from human players at their substations to deliver power to the grids in their community. Each community contains 3 grids. The center grid is the cooperation grid. A link is a line of 3 game pieces scored on the same row. Completing enough links earns the alliance a sustainability bonus. If each alliance scores at least 3 game pieces in the cooperation grid, the sustainability bonus threshold is lowered for both alliances. Robots are protected within their community and loading zones. As time runs out, robots race to their charge stations. Alliances earn points for each robot docked to or engaged with the charge station. Earning enough charge station points earns the alliance the activation bonus. The alliance that earns the most points wins the match.
All right. Okay. So looking at our 2023 game, it's definitely very different from Crescendo. This is what we call a pick and place game, as opposed to a launching game. So in these games, your basic objective is to grab an object from one part of the field. In this case, we have our loading zone over here for the Red Alliance, and then we have to take the object over into what they called the community this year, into our protected zone, and then score them in different places along this grid. And so in almost every FRC game, we have what are called cycles, where we're basically doing some form of repetitive task as fast as possible. In other sports, you might call it a possession, but since we have multiple game objects, we don't have turnovers in the same way. If you play basketball or watch any of those other sports, they're similar to those things. But it's basically when we're going to go get a new game object, take it down the field, and then score it, and then we're going to repeat that action. And so part of our goal in basically every game that we're doing is how can we perform those actions as fast as possible. And that is one of the things that drove 3005, the robot that we're going to look at tonight, to design their robot in the way they did, was how they analyzed the game and the way that they wanted to play it to try to be as fast as they could at scoring those game objects. So what are the kind of tasks that we have to be able to do? So the most of the there's often a very complex strategic analysis of the game, like what is the next best action to take or every time you're doing something. Those are all super important. But when it comes down to it, what the robots have to do is largely pretty simple in the abstract of just, if we had a perfect robot that could do everything, what are all the tasks it needs to do? For the most part, they come together pretty quickly. From that video, you could see what has to happen. The robot has to be able to pick up cubes and cones. The majority of robots that were very good in 2023 were absolutely able to pick up cubes from the floor quickly, and then they could pick up cones either from the human player station or the floor. And this matters somewhat, and we can talk about the strategy a little bit, was basically in autonomous mode, you had these starting objects that are on these little dots. They're not in this picture, but they had to start here on the floor, and you could choose whether those are cubes or cones. So to be able to have a good autonomous mode where you're scoring multiple game pieces, you need to have a ground intake of at least one object from the floor. And then during the match, it was okay for most teams, depending on how you played the game, to either go to one of the two human stations and grab the object from either the shelf or from the single substation where you had like this ramp that would drop the object into your robot. And so either of those were pretty acceptable. And then also you could throw the objects down to the floor from this station as well, so you could end up getting some of the objects out over here or standing up even right here. So there were some different ways you could choose to grab the objects from the floor or from the station, and that kind of depended, that ended up resulting in how your robot ended up behaving. Also, some of who you were compatible with. You wouldn't want 3 robots who all needed to be able to score or to like grab an object from the same substation. So if all 3 of you needed to get the same cones and cubes from this ramp, it would be really hard to run an alliance that way, as you'd all have to take turns coming into load and then going back to score. So the more that you could be using kind of different areas of this loading zone for your alliance, the better you were. And so there were some robots that could load from different versions of it, so they would be more flexible. Or if you could load from the floor, you often could get from places that weren't in the way of other people. And then you need to be able to score the cones and cubes on all 3 levels. So basically, if you were just a drivetrain and you could just push game pieces around, you could pretty much score them in the low goal or in the level 1, which is pretty easy to do. And then it took a little bit more to reach up and go into level 2. And then the third level, the furthest one, was actually a challenge that we hadn't really had before until this year, which was reaching out away from our robot. And so the amount of reach you need to only have your robot get stopped here at these kind of protectors and then reach all the way out to the cone was pretty far to get to score the cone nodes out there. So that was one of the biggest challenges of 2023, was how do you build robots to do that. And then at the end game was relatively easy this year, where you basically just had to balance on this bridge. It pretty much became a solved problem pretty quickly. Some teams had like some software to kind of auto balance, but really when you needed that for autonomous mode because you could balance at the end of autonomous mode. But actually in match, it was relatively easy to get 2 or 3 robots stable and balanced on the bridge. Just having your pilots do it wasn't actually that difficult to do. So tonight we're going to look at one version of a very competitive 2023 robot from 3005, the Robochargers. So kind of like we talked about last time, robots are broken up into mechanisms. So we're going to look first at their drive base. Cool. So relatively simple swerve drive base, very similar to what most teams are running. The motors we use are called Krakens. They have integrated motor controllers into them. The Neos and Neo 550s that this team uses do not. So these little boxes here are what control the motors that they're using. So this is a pretty standard chassis using the Rev swerve modules. They have a much smaller footprint, so they take up a lot less space than some of the other what we often consider like full-size modules. So the Swerve Drive Specialties, MK4Is that we use on our past robots, also the West Coast products, Swerve X and Swerve X2 modules that were just released. And then ThriftyBot has come out with Thrifty Swerve 2.0 modules as well that are all in a pretty similar space to the modules that we currently use. So they take up a couple more holes here and are kind of like this full triangle of this corner, where here we're able to package it a lot smaller and then only have the controllers kind of sitting off to the side, where you could move these if you needed to. If you needed the space for something, since these are only attached with wires, you could have them mounted somewhere else, back even over here, and like run the wires all the way out if you had to. So they do have some advantages, especially on space. They have smaller wheels, so they run a 3-inch wheel, which at different points they had some different types of wheels. Some of them were having issues where the rubber would come off. They've fixed that for this season. The wheels for these modules work a lot better. And so you can still do that, but you have a somewhat fewer options of the types of wheels you can run. And then they're only 1 inch wide instead of 1.5 or now even 2 inch wide on some of the bigger modules. But the frames are pretty much standard. They run these 2x1 tubes with this 1/2 inch hole pattern. So every hole on here is a 1/2 inch apart from the next. And this really just gives us a lot of mounting options to move things. If we design something early and we end up needing to add some functionality or something or some part to the robot, having all the holes there already done normally makes that very, very quick to add. One of the things they have here, they have these little blue parts, and these corners jut out as well. These are what we commonly refer to as legalizers. The way the bumper rules work, you have to be your frame has to be a certain distance away from your bumpers. The wooden part that we talked about are kind of like the robot pads. And so these allow you to meet those rules explicitly. These are likely just 3D printed parts that they riveted on. Similar here, this is like a 3D printed cover. It's able to protect some parts of the Swerve modules. And then they have a pretty standard rest of the system. They have a belly pan. They actually dropped a portion of the belly pan, but not all of it. So if we look in from the side, this upper part is just normal, attached right to the 2x1 bottoms, and they actually dropped down the belly pan portion that holds their battery. That's so they could get their battery kind of below the level of this frame, while still giving them enough clearance to drive up the ramp during the end game, or during the game, anytime they needed to drive up and over the ramp. We can pull bumpers back on. Maybe we can pull bumpers back on. What do we need to do? I did hide all instances, and now everything's hidden. There we go. Bumpers are back. Okay. So we can see how the bumpers work here. I don't know if we have all of their mounts on here. Okay. Oh, that's the whole rest of the arm. All right. Okay, it just showed everything. That's fine. Here we go. Okay. So it also has their bumper latches. This is a relatively common bumper mounting solution. We've used this before in the past. I think back in 16, maybe we started this, 17. Almost certainly 17. Our 17 robot and I believe 18 both use similar latches. Sometimes they work well, depending on kind of how we want to do it. But these basically just allow you to slide this back on each one of these like 4 latches that go over these pegs that are mounted into the robot. And they just kind of snap into place, and they hold your bumpers on. So depending on exactly how much space or size you have to fit everything, and again, bumpers, we know bumpers are, the whole rule set is getting overhauled quite a bit going into next year. So we'll have quite a bit of options in how we mount bumpers going forward. These are definitely still an option, but they're potentially not as useful when the restrictions are a lot looser next year. All right, let's look at the arm mechanism. This is a really integrated robot to where there's not too many mechanisms going on. You basically have your drivetrain, and then coming up, you're going to have the rotation part of the arm, the extension part of the arm, which we'll look at, and then the intake that has a couple of interesting features on it as well. I'm going to go ahead and hide that. Okay. And these little floating guys too. Cool. All right. So looking up at the arm, this robot ends up having not a ton of structure at the top. So they did a lot of work to keep it very light. They didn't have any large A-framing or anything. They basically have these two main arm supports coming up here at an angle. And that's pretty much all the main structure that they have for this. And then what they use is kind of like a suspension bridge. They're using tension members, so they have these that they're able to tighten on each side. I don't remember if they were using steel cable or if they're using cord here, but either one of them works. These ones are probably steel cable, it looks like. That would be my guess. And so you can use relatively thin steel braided cable. It has very fine strands in it that allows it to be somewhat flexible and allows it to be very strong under tension. So when basically you're stretching this cable out, and if you do it on all four corners and stretch it out, they act against the forces the same way that having a bunch of like actual support arms would. So where if you actually wanted to come in and like have a full A-frame tube, if you wanted to put more metal here like aluminum rods or aluminum tube going down to the front or back, you could do a very similar thing, but it would just weigh more. Where with these tension setups, you can adjust how tight they are by turning these turnbuckles. These are similar to what we use to like tension our chain. They're just a little bit bigger and they're designed specifically to run with cable. And if you have all four of them done, if you go and like if some force was trying to push back on this arm and wanted it to move backwards, you would be pulling these. And since they're already tensioned and they're already tight, they're not going to expand easily. They're not going to stretch. They're not like rubber or anything. And so since they can't stretch, you can't have this thing get pushed back. And the same thing happens if you have some force here pushing forward. You can't stretch these ones as well. And the same works for left and right. And so for a relatively limited and very lightweight structure, you can still have an incredibly strong overall mechanism because you have these cable runs in place supporting the entire structure. And so they have some specific places where they do these standoff, and they have the bolts on top of them. So they have those all designed into the mechanism, so they know which side of everything where it goes, how it's not going to have too much angle, or how big the washers need to be to support it so it's not moving around too much. So they did a very good job of designing this in and making it work for them. And then even being able to use the cable to mount things like some protection here, sponsor panels most likely, without needing to have the full rail or anything there for it. So this is a very, very light system. If you have something that's going to be very tall, or just need it to be very thin and out of the way, this works really well for that. Okay, so the main actual arm joint that does the rotation. So what this robot's going to do is it's going to be able to pick up its arm and rotate it forward and backwards. So it can start over here, put its intake out, which I think I can bring back. It can put its intake out. It can grab a game piece from the floor. And then it's able to flip its arm all the way over. If I can get OnShape to cooperate. Let's see. There it goes. It can flip its arm all the way over. And then it can score from this backside position as well, or the extended backside position to reach even further. All right. I was looking for the button. I don't know where the button is. Okay, it's fine. Let's try to get it back in a reasonable position. Okay, so this arm pivot joint is powered down here on the gearbox. So they have two Neo motors on this gearbox. That is just a single gear reduction. So they have the two gears coming right off the motor. When we have the gear right on the end of the motor or whatever gear, sometimes a pulley here, we always call this the pinion, the one that's going to be directly on the motor. And so this is often going to be a small gear because like we talked about last week, one of the main principles for doing pretty much any amount of motion in robotics is that the motors are often spinning way too fast for it to be usable. And so we want our actual output to be geared down. So we have a small gear or a small pulley or a small sprocket here. And then we have the larger one here so that for every one rotation of this gear only spins a quarter of the time or whatever the actual ratio is. In this case, we could go in and figure it out. So we know this is a 10-tooth pinion. And this is a 68-tooth gear. And so the math is really easy. It's just division. It's 68 over 10. So for every 6.8 times that the motor spins, this gear only spins once. So that also means that the torque output, rotational force basically that we have, is multiplied by 6.8 at this shaft. And so then they're able to gear it more. So down here we have a sprocket. The other spacers here, we also have the part number printed into the spacer so they know which one it is, which is nice. So instead of if you have two things that are very, very close together, they have it just embossed directly on the print. So you should have the same thing on this one, I imagine. Yeah, just down on the other side. But yeah, so they have the part numbers directly printed into the spacers, which is very nice quality of life feature. If very quickly you have to reassemble something in the pit before a match or something, you know which spacer goes where, and you're never having to like figure out exactly which size it is, have to pull out calipers or measure them. You can have it printed directly into it. Okay, so the other part of this gearbox, so I guess we'll come back to down here and how this works. So the sprocket here is a small sprocket. The gray blocks up here are chain, and they come up into this much larger sprocket that they have up at the top. So this is a very, very big reduction. So we can kind of see a little bit what it is. So yeah, so it's one of their custom parts, so it's just numbered by their numbering system. So I don't know exactly how big this is, but you can imagine this is a much larger reduction because it's basically just the ratio of diameter from that large one to this small one, because they never actually need this arm to spin a full revolution. right? It can only ever go from here back to behind itself. So they want to have all of the torque they can to make it much more controllable. And that's a big part of one of the big important things that we're trying to do while designing robots is mechanically you want to build the robot in a way that the software and electrical team can then actually control it comfortably and be able to put it into positions very easily and things. If this sprocket was a lot smaller, if you had less motor power or less gearing, it's possible that the arm could still move back and forth. Like, it might still be capable of doing it. It would just happen in a way that would be much harder for the software team to be able to control. So a lot of times when we're doing the math to decide exactly how we want a ratio to be, part of that is thinking, okay, how fast do we need this arm to be able to spin from the floor back to behind us, and then doing it in a way that's efficient for energy, so we're not using too much of the battery to do it, and is controllable in software, so that when we tell it to do it, we can do it and stop at very fine positions, and know exactly where we're actually... So when we tell the robot arm to do something, to go to a certain degree, it actually goes there, stops, and works perfectly. Okay, so because they have this really long run of chain, even though it is steel, it stretches, so you need to have some form of tensioner on it, or as soon as you build it and you start running it, it'll stretch enough to where it's possible for it to jump off the sprocket, and we don't want that. And so the way that they tension this gearbox is because the gearbox is actually only mounted on this single pivot tube, and then it's tied in back to the rear frame rail with these two turnbuckles. So these two devices are the same type of devices up here. They have one of these threads is left-handed, one of them's right-handed. So when you turn this, it either tightens both of them or loosens both of them. And in that way, you can pull this gearbox down, and it'll pivot around this pole and get lower and add more tension to this chain. So if during competition you start seeing that this chain is loose, all you have to do is turn these two turnbuckles, and now you can get a much tighter chain. This ends up packaging very well. The gearbox ends up almost just floating. You don't have to have a bunch of other sturdy mounts for it, since you have this part in tension here, and you're using the chain tension itself to hold it. It's not like this is going to flop around at all. And you're able to have a rather strong tube here connecting across the whole assembly. I don't know if they show... Yeah, so then the way they mount this is with this little part here, which is called a tube insert nut. These are used in a variety of situations. Some of the larger ones end up being used on parts of bicycles to hold the handlebar and things on part of the stacks of different bikes. Sometimes they'll get used for table legs and things. But basically, they have these steel little flanges, the black part here, that are able to be pressed and compressed into a tube as you shove it in one way. And then if you try to pull it back out, these little corners try to dig into the tube and stop you from pulling it back out easily. And so it's a relatively simple way to mount a round tube into your assembly. So this bolt here is what's bolted into that tube insert nut. You can also put those into the ends of some square tubes. They make different ones, but they're more commonly used for round tube, and we've used those a good amount in the past, and they do work pretty well. In addition, they actually mount their radio to the same tube, the radio and radio power module here, so they have a little 3D printed adapter that lets them just clamp this on, and then I imagine this is some amount of foam to kind of shock absorb it, so they're not getting as much vibration through their radio either, because you don't want the radio to restart in the middle of the match because you shook it too hard. And so this is up out of the way. It's not near, it's not too close to any motors. You have the motors here, but they're not that close to it. And you can easily see the lights, easily grab it to program it at the event, anything like that. And we'll be running the new radios next year, so they won't look exactly like this, but they're similar rectangle brick, just black now. Okay, so going back up, we can start looking at how they did the pivot as well. So this is a pretty nice way to do it. So they have these plates that are riveted into the 2x1, and they are capturing this bushing. And what's cool about it is instead of just putting a hole in a single plate, let me grab a section view here. Yeah, perfect. Okay, so instead of putting a hole in a single plate, so like both of these could have been just one single plate and they could have shoved the bushing through, and that would have been really strong. It would have worked great. You would have had no issues until you wanted to change the arm. If you wanted to change the arm, you'd basically have to somehow either take the whole thing apart or hammer this tube through the entirety of the arm assembly to be able to get it all apart. And that's really frustrating. You don't have enough time. If you're in the middle of playoff matches and you're trying to get the robot back up because something broke, you want to be able to do this really fast. And so these bolts right here give you the ability to do that, because if you just unbolt these lower two bolts, this whole upper cap comes off, and now the whole arm, bushing, and everything can be taken right out the top of the robot once you remove the chain. Probably unbolt a couple other pieces that are mounted on. You have to deal with the wiring and things, but it still allows for a lot more maintenance than it would if you had to somehow shove this tube through and then like reinsert it. Without a noticeable loss of strength that actually matters. You're still not going to be ripping through these bolts at all through any of the weight, and still, especially since most of the weight of the arm is still going down, right? Gravity's always acting on it that way. We're not too worried about the top unless it's coming out for some very, very bad reason for something. If it's getting yanked on, this robot's not having to climb from this. We're not suspending the entire robot from this. Even if you were, this would still probably be enough. You might want to add another set of bolts or something. But you'd probably be able to get away with just this. Okay, so this is that pivot shaft that's being captured there. We briefly talked about bushings last time, but just a reminder, so these are also known as plain bearings. So these are made of like a brass. They normally have some sort of oil embedded inside of them, so as it rotates, it gets lubricated so it can slip. And largely, these are just much more inexpensive than ball bearings, and they're also way more space efficient. A ball bearing for this same size tube to be able to spin inside of would be much, much larger than this bushing here. Would be much heavier, and just isn't needed in an application where we have enough torque to overcome any of this friction, so it's able to move smoothly anyway, and we're just not spinning very fast, where we're not going to be generating a ton of heat in this motion either, or at least continuously not very fast. Okay. The other part of this pivot that might be interesting is this little bracket sticking out over here. And so what that is their absolute encoder mount. So this is a rev through bore encoder. And so this little device lets us, or lets any team, very quickly know where a shaft is that's positioned inside of here and where it's rotated. And it can do it in absolute units, which means when it powers on, it knows which way it's pointing. And so even if you start the arm completely vertical or completely down or in any position, the robot can know where the arm is at boot, at startup, and then from there be able to send it to wherever you're actually telling it to go. So this is a very convenient way to do that. We did something similar on our pivot this year, so we could start it up in any position and the robot would know where it was. And you also just get more accurate feedback control for the programmers because they can know the exact angle of the arm without having to go through any of the gear reductions and things that the motor is. So if you're using the internal encoder of the motor, you would be spinning, dozens of rotations for every time this needed to move a little bit, where here we know we're spinning only that portion of the rotation that we're worried about and actually directly controlling. All right. And yeah, so they have a little tiny bit of hex shaft mounted here in this, using one of the hex tube adapters that they pressed into there probably, and then just a little hex shaft. That actually might just be a full part they made, it looks like. Yeah, so this is actually a full printed part, and they just printed the hex shaft on there. So instead of having a piece of hex shaft, they just printed this entire thing. Yep, and with it embossed the part number again. So any of their prints, they can do that. They always leave it there so they know what part number a print is. And then this just goes inside the encoder. So you don't need to have the aluminum shaft there. It's not taking any real load. All of that's being transferred through this. You wouldn't want it on the encoder. So this is a little bit lighter to just have it as a printed part. And that works great. Similarly, they have some more what look like lightly probably printed parts, almost certainly. They have these chain guards on the outside so the chain can't skip off at all. And so those get bolted to the big custom sprocket that they made. So this spacing and everything is there so they can have their different mounting points on it. Anything else they need. Should be able, I'm trying to figure out. Yeah, so this is part of how they're able to mount to the actual arm. So this printed part here mounts to the sprocket, and then this clamps along this tube. I'm not sure if they get it any other place. So it looks like you have the sprocket part here. The opposite side from where the sprocket part is just a piece of polycarb. We can see it's translucent in CAD, so we know this is not going to be metal. This is probably smoked polycarb, which is like a translucent gray color. And it looks like it just goes through that at the 1255. That's probably similar. Yeah, so that's still going to be a relatively nice fit there. And then they just clamp on again. I don't know if there's anything else transferring any torque there. It doesn't look like it. But it would be relatively hard for that to slip. But not impossible, but probably not. I don't know if they may have at one point pinned the tube through here so you could drill through one of these holes and put a bolt through there if you needed to. That may have been an option that they were considering but didn't need to do. The clamping was enough when they bolted down this bolt here. That gap gets smaller and clamps to the tube, allowing it to rotate cleanly with the whole arm assembly. Okay. So let's look at how they do the extension. So kind of built into this sprocket, we can see that we start seeing the different bits of bearings and some bolt holes and things because they actually use it as the gearbox mount for the extension. Let me see if I can make this a little easier to see. I'm going to hide the cable chain. Okay. So we have, again, a relatively simple single-stage gearbox. We have the pinion on the output of the motor. We have the larger gear here, so we get that nice gear reduction again. We can look through. So this is a 64. I'm guessing this is a 10 again. No, this is a 13. So it's a little bit different gearing there. So not entirely sure why they decided to go that route instead of getting something even smaller. There may be a packaging issue there, some reason why they needed it to be a little bit further away. Possibly because of this belt, actually. This is probably why. So my guess is if you mounted a 10-tooth there and had this same gear, the motor would have scooted in just enough to be able to hit here. And you wouldn't want that. That's only just from looking at the CAD. No real idea if that's the exact reason why, but that's probably why. But you still get enough reduction there for this linear mechanism because you have this pulley that's on the output here, and it's driving this really long belt. And it's driving this belt down to a sprocket. And so the sprocket itself is what's doing our linear motion. I'm going to hide some things again. Let me hide the drivetrain and the bumpers. Do that quickly. Bumpers. Okay. So we can see under it. All right. And so you have another sprocket, and then they've turned this bit of chain here that they have mounted to this tube into a rack. And so this basically is like a linear gear. So instead of the chain wrapping around the sprocket, it's just moving along the individual teeth of the chain mounted here. And it's doing that to be able to extend and retract this whole assembly in here. So it's able to fully extend it and bring it back just by spinning this sprocket in the little chain teeth down here, or in the sprocket teeth in the chain down here. And so every one rotation of this sprocket moves it basically the circumference of the sprocket, roughly. And so it's only a few inches for every circumference, or for every rotation, and it needs to move a pretty good amount. I don't know the exact amount of extension this has, but it's a decent amount here, 20-something inches, probably. Let's see, 20.5. And so with that, you have enough control from the motor and gearing to need your 4 or 5 revolutions total of that sprocket to extend it the whole way. And that should be controllable enough, and was, since this was a competitive robot. Okay, a couple other little things they did. So because they have this really long belt run, most of the time with belts, we don't have to worry about them in tension too much for most of our small belt runs that we run for like our intakes and things. The belts that we use have fibers running through them that don't stretch very easily, so the belts don't grow in the same way that even the chain does. You would think that it's kind of intuitive to think that the steel would be harder to stretch, but just because of the way they're assembled and the way the whole assembly works, the chain actually creeps and stretches a little bit more than the belts will, since they have these fiber cords running through them that prevent that stretching. But when you have a really long run, it's much harder to account for that, as even little things like if this plate or anything started bending a little bit, or you just didn't get everything exactly right with the rivets and holes and stack up and things, you can have a little bit of gap in things over a long distance. And so they did build in a chain tensioner here that allows them to loosen up a few bolts, slide this tensioner in, and then tighten these back up, because they have a single slot in the part here, and then they have the longer slot, if I can find it. Are those also holes? Oh, yeah, okay, so those are also holes. This is what you get for doing this live. And so, again, I've not actually looked through this robot most of the time, so a lot of times I have to figure it out along with everybody else. There they go. The slot is down here at that curve. I just couldn't see it earlier. And so you have this slot right here. And so what they're able to do with that is they can move this bolt into any of these other holes, and they can adjust the tension on this setup. So this is one of the looser ones. They could take this out, loosen these two, rotate this down, and start pushing it in further, and you'd be pushing the belt down further to add more tension to this belt. So if anything starts to creep throughout the season, you have it built in here to be able to have a bunch of different settings for where to put tension. These are kind of all on this like arc that you can kind of see forming here. So this gives them a lot of different options. They would know what the next hole over was to be able to adjust something to add a little bit of tension from this pattern that they built into this. So a lot of those are things, again, that we're talking about. It's relatively easy to make a robot that does a task. It's very, very complicated to make a robot that does the task extremely well and then also works throughout an entire season, can be repaired, can be upgraded. All of those things go into our engineering design process to make a more competitive robot. Okay, so we're going to quickly go through how the extension works, because it's kind of just the same bearing package that we've seen in elevators and things. They, again, just have roller bearings on the bottom stage of this tube here that are sliding on all of the inside walls along here. And again, the bearings reduce friction, make it slide super easily. And then at the top, out on this side, so extend this out, we can see that they have bearings on the sides here on each side of the tube. They, again, have bearings, and they have, they're able to gap them so the chain can come through nicely. Similarly, they have some other parts that have to come through up at the top. And so they use that same kind of gap method. You have a slot here in the external tube for it, so it's able to slot in. So when they're going down to actually intake, this whole arm is very supported. It's brought back in fully. And it is not going to bend or break when it's out as an intake in the middle of the field. But once they go and extend it when they need to score, it's a little bit weaker there, but you shouldn't be running into things at that point. All right, let's look at a couple things. So the last bit of the extension that we hadn't talked about here is how they do the cable management for the extension. So they have a cable chain that's going to be mounted to the arm. They'll have a plastic cable here, and then it's able to get like folded back up inside this tube. So as it comes back, it gets folded up and held in here, so it's not swinging around or anything. And so that's where the wires are to be able to extend out to the motors that they keep out on the end of the arm. All right, with the last little bit of time we have, we're going to talk about their intake specifically. So their intake was one of the cooler ones this season, because what they figured out they could do is when they came out and they extended out the arm and they put it down at the floor, they were able to use these two wheels to intake both cones and cubes depending on which side was facing down. And so in this configuration right now, this is their cone pickup configuration. So they would pick up tipped over cones. So the cone would be on its side, and they would basically almost pick it up like a log. And so they wouldn't worry about which side the flange was on, because they have this pivot joint here, or a rotating wrist, that allows them to spin this whole contraption upside down. I don't know if it does it in CAD. It doesn't look like it does. It would be free spinning right now, or at least doesn't do it in this configuration in CAD. But this allows them to spin this over 180 degrees, so that they can pick up the cone, and if the flange is over on this side, they can flip it 90 degrees and have it be able to score and put the cone facing the bottom, or if the flange is over on this side, they can turn the other way and do the same thing. So no matter which way the cone is, they're always able to place it on the little stick that you have to score it on, because they were able to rotate their wrist. And that was one of the more challenging design choices that a lot of teams had to decide, was whether we wanted to be able to manipulate a cone in that way, because it wasn't a symmetric game object. It's not like a ball where you can just score it in any configuration because it's all the same. The cone itself had clearly a very one-sided way it had to be scored, a single orientation that worked. And their robot did that very, very well to be able to pick up a cone smoothly from the ground and then place it back on depending on which way they flipped the wrist around. And then when they flipped this all the way over and put this part towards the ground, the cubes were able to be intaked into here, basically acting as a ball. They were cubes, but they were inflatable. And so once you did that, they pretty much worked the same as any foam ball or anything. And so it had a very lightweight outer frame here. These wheels have these cutouts in them. These are called compliant wheels. Because as you can like push them or squeeze them, these little cutouts can fold and bend, and so they mold to the shape of the game object. Similar to these ones down here, they do the same thing. These are just from different vendors who make different ones. And so they're able to do that same concept. So that's what we're looking at, to be able to intake the cone through here, sort of just grabbing a cone the same way you'd grab it with your hand. They're just doing it with rollers here. And then similar, doing the same thing with a cube. The motor packaging to be able to do this rotating wrist and then also drive the intake is pretty cool. It uses a good amount of 3D printed parts out on the end here. But we can start looking at the one in here first. Let me hide this mount. So this is relatively simple. So this is a Neo 550. It's a really small brushless motor that Rev sells. Into an ultra planetary. So this is a tiny gearbox that's often used in FTC robots, but it mates well to the Neo 550. And then they have a small printed adapter here to mount the shaft off a little bit. So this is an adapter that's sold that lets you go from the ultraplanetary to an 8mm round shaft, which is like the same shaft size that the full-size Neos use and some of the other motors use. And they're just able to put the pinion gear right here at the end. And so that spacer block just lets them hold this housing in here without having this rub anywhere and without having the shaft get too long to be able to run into things. They had some extra space here at the back end, so it was easy enough to do that. In addition, they have this part here is like a printed cover. Stop anything from hitting this. The Neo 550 itself, this outer shell does rotate. So this part up here where the face is fully mounted, but this is part of the motor and this will spin. And so you don't want wires or anything touching this, or even people's hands. It is spinning very fast sometimes. So guarding it is pretty good. They have some zip tie holes here, probably for wires. So you can run a zip tie through this channel. So all these details are into their 3D printed parts. They cost basically nothing but a little bit of print time, and it allows your robot to be more functional. So if we can design things early and then do a lot of design work to make things better, and we can iterate, you can design in a lot of features like that, especially when we're using 3D printed parts, because it costs very little to add 3D features like this. Compared to if you were doing this out of a sheet of something and you try to cut this out, that would be really, really complicated. But it's something we can definitely do when we're printing, since we're just adding plastic and layers going up. All right. So again, we have this wrist joint here. We can actually look and see how the wrist itself works. Let's see if we can scoot this out a little bit. I think it's probably easier from this side. So this is just an aluminum tube, 1.25 inch square tube. We can check what the wall size is. So it's 16th wall. So we have a inch internal square in there. When we hide that, we can see we end up with a block that they made here and some more printed parts. So this is another printed part. This blue is almost always going to be printed on their robots. And so this was basically in there to be able to hold the bushing on the back end of this tube. And then they have an aluminum tube here as well. If we isolate this, yeah, it does look like they did all of that as one part. Yeah, so that's probably one of the most complicated machined parts on this robot. So this looks like they could have done it in different ways, but the most likely this was done fully as a billet of aluminum. So this started as basically like a big rectangle of aluminum, and then they had a most likely a CNC mill come through and remove all of the parts of the aluminum they didn't need, right? So they cut away all of this rough cut part, leaving this plate and these blocks, and then they came in and added the features afterwards to drill through, to add these drill holes all the way through, similar to the ones through here and through here. These ones are tapped, so those bolts could mount to it. Then they turned it over, ordered it on a machine that could turn it over on its own. There's, depending on what type, how expensive of a mill you have and what features it has, you could have a part that the mill itself can turn the part over. They machined in these interfaces as well, mostly for weight lightening, I imagine, and they could do it, so they did. Yeah, but again, you have the same sort of bushings here for relatively slow rotation, where you could have a bearing, it just isn't nearly as space efficient, and here they're very much worried about space to be able to fit everything into that joint. All right. Yeah, and you can see this is how they actually bolt this whole assembly through into here. I don't know if there's, let's see, did they... Oh, there we go. So into this 3D printed part, they have threaded inserts. So these are metal threads that you heat up and you can press into a 3D printed part. So that's how they're able to bolt that together. And it looks like those get bolted in somewhere in there. We can kind of see where. Oh yeah, they actually just get bolted in right there to the tube itself. So that's interesting. So what's the easiest way to see how that works? We can probably section view something, maybe here. Nope, that's too far away. Inner wall, let's go that one. Except backwards. Arrow. There we go. And slightly farther. There we go. All right. So because these have these holes up here, before they insert all of these tubes and things, they're able to put these bolts in and secure it into place, and then they can put the tubes back on top. So if these ever did loosen or they need to work on them, they would need to pull this shaft out to be able to get these bolts back in. They'd also probably need to take this gearbox off as well. So this is definitely a pretty space-constrained whole unit here that they're working on. And to wrap up, we're just going to look at the intake motor mount as well. So we can see inside of here and behind this plate, they have a gear that mounts directly to the ultraplanetary output that the Neo 550 is running. And so this gear specifically does a couple things. So it drives this custom gear that they have here. And so they have a couple little spots for it and plates for it and things to be able to have bearings everywhere. Most of the bearings are riding, these are basically a dead axle, so the bearing, the shaft itself is basically this entire gear. It's spinning on these bearings that are sitting on these bolts, so the bolts aren't moving at all. The inside of the bearing isn't moving, the outside of the bearing is spinning quickly, and so because of that, we don't want it to be a bushing, we want it to be a bearing. And then they have the rest of the gear chain here actually connecting all of these gears together to power all of these rollers. And then a similar thing up top. You have 2 gears here, and then a belt driving out to the front here to power this, to power these rollers that do the main intaking for the cubes. Again, they use some pretty clever 3D printed parts here. This part is a guard for the whole thing that they're able to print as one piece. Add some like standoffs into here. They were able to put like a hex shaft in here as a standoff. Same thing they did in a lot of these places. They use hex shaft standoffs, and this whole print goes around all of that. So if you did need to take something off, you would need to take this side off of the whole unit to be able to get it to the inside of it, because you wouldn't be able to just take a single standoff easily without removing this whole outer plate. But it does give it, it's very robust. Things aren't going to get inside those gears or into that belt at all. And it gives you some mounting points for some of the other parts like the cube arm assembly and things like that. They did do some of that as 2 different parts, or parts that go on the inside, so they're able to iterate that a little bit. So they ended up wanting to change how the cube worked, and how, like, if they wanted to change the shape of this at all, they could do that without changing the whole rest of the cone intake down over here. So you're able to change throughout the season, iterate, make it better. And so there's a lot of design work that goes into having a robot that's functional and allows you to accomplish all of your tasks throughout the entire season, not just something that works once, but is fully buildable and maintainable all year long. All right. I think that pretty much finishes up the 3005 robot. They have some other basic things. This is probably the camera mount. Some basic RSL mounts going on the inside here. These tubes were for LEDs, I believe. So they have LED strips running inside of here so they can do feedback to their drive team. But yeah, overall, a very, very clean and simple robot. Oh, the one part we forgot to talk about, I'm going to do really fast because I've skipped it when we were doing arm stuff. This piece here is a gas spring, or sometimes called a gas strut. This is the same thing that's on like the back of your SUV's hatchback to lift the liftgate up. And so these have compressed air on the inside of them. And so they're always trying to extend this rod with some certain known amount of force. And so in this case, they're using it to counterweight the arm. And so even when there's no power on the arm and it's sitting out here fully flat out, and it's pushing down, trying to fall back down to the ground because of gravity, the gas spring here is always pushing up on it. So if you do your calculations correct, you can make it to where the arm is nearly weightless for the robot. You don't really need to get it perfect. Assisting at all is very helpful. So having the spring assist helps the robot hold it in place, so it uses a lot less energy when it needs to hold the arm at a certain position up in the air, because the gas spring is basically helping it push it up at all times. The very clever part of the way 3005 did it is because the lower pivot of this gas spring here and the main pivot of the arm share a direct line. If I get back to the right side, okay. And the way they mounted it, it's able to push up the entire way until max height. And then because there's no like extended pivot bar all the way through or anything, this doesn't run into anything. Even as it comes back down, it's still doing the same thing, right? It goes, this is what we call an over center mechanism. It crosses the pivot point. This linkage bar right here basically crosses our pivot point. And so as it's working down the other side, this is still always counterbalancing gravity, trying to push up the arm. No matter where the arm is, the gas spring is always trying to push it up. And so this makes it much easier to control. because it has that spring assist the whole time in. So it makes the robot think that the arm's a lot lighter because it's not, the motor's not having to lift all of it all the time. The gas spring is doing a good amount of the work, right? It would be a lot harder to lift your tailgate on an SUV if you had to lift the entire thing every time. If you ever take those gas springs off, don't do that on your actual car. But if you ever need to for some reason, if something breaks, if you're working on it, it gets a lot heavier if those aren't there. All right, I think that covers the entirety of this robot. Thank you, everybody.